Hello, everyone, and welcome to this deep dive exploration of two of the most powerful concepts in artificial intelligence: the Bellman equation and the Markov decision process. You've probably heard the terms tossed around in machine learning or reinforcement learning discussions. Maybe you've even seen a few formulas or diagrams that looked more intimidating than enlightening. But today, we're going to cut through that fog. We're not going to memorize formulas or recite jargon. We're going to truly understand the core of how intelligent systems make decisions, whether it's a self-driving car, a recommendation engine, or even a robot learning to walk. At the heart of intelligent behavior is one simple but profound question: what should I do next? To answer this question, machines rely on logic, probability, and planning, all wrapped up beautifully in something called the Markov decision process, and refined even further through the Bellman equation. In this solo session, we're going to walk hand in hand with these ideas. I'll explain what they are, how they work, and why they are so central to modern AI. You don't need to be a mathematician to follow along. Just bring your curiosity and a few minutes of your focus. By the end, not only will you understand the principles behind some of the smartest systems in the world, but you'll also appreciate the mathematical poetry that underlies the intelligence we're trying to recreate in machines. So let's get started with the first building block, the Markov decision process. Understanding Markov decision process. Imagine a robot in a grid world. It can move up, down, left, or right. Each cell gives it a reward. Some cells are dangerous, others are rewarding. The robot's goal is to learn how to navigate the world to collect the highest reward over time. That, in a nutshell, is what an MDP models. What is a Markov decision process? A Markov decision process, or MDP, is a mathematical framework for modeling decision-making in environments where outcomes are partly under the control of the decision maker and partly random. An MDP is defined by 5 components: states, S. These represent every possible situation the agent could find itself in. For example, each square in a grid world. Actions, A. These are the possible moves or choices available to the agent in each state. Transition, probabilities, P. These represent the likelihood of moving from one state to another given an action. In real life, actions don't always work perfectly. A robot trying to go north may slip and end up going northeast. Rewards, R. This is the feedback the agent receives for taking an action in a state. Rewards can be positive, like finding treasure, or negative, like falling into a trap. Discount factor, CTG. This is a number between 0 and 1 that tells us how much we value future rewards compared to immediate ones. A value close to 1 means we care a lot about the future. Put together, these elements describe a world where an agent observes its current state, chooses an action, transitions to a new state with some probability, receives a reward, repeats the cycle. The goal of the agent is to maximize the total reward it expects to receive over time. This brings us to the idea of a policy. What is a policy? A policy is a strategy. It tells the agent what action to take in each state. Mathematically, it's a function. PS. A. It tells us, in state S, do action A. But here's the tricky part. Not all policies are created equal. Some are short-sighted, some are greedy, others are long-term thinkers. Our goal in reinforcement learning is to find the optimal policy, the one that brings the maximum expected cumulative reward. But how do we know if a policy is good? We measure it using something called a value function, the power of the Bellman equation. What is the value function? The value function tells us how good it is to be in a certain state, assuming we follow a certain policy from there onward. There are 2 common types: state value function VS, the expected return starting from state S and following policy P; action value function QS, A, the expected return starting from state S, taking action A, and then following policy P. Now imagine trying to compute these values across all states. It sounds expensive, right? This is where the Bellman equation saves the day. Enter Bellman. Richard Bellman was a mathematician who developed a recursive way to break down these value functions. His insight was brilliant. Instead of computing value from scratch, we can express it in terms of itself. Let's simplify the idea. Imagine you're in a state. You take an action. You get a reward. Then you end up in a new state. From there, your future value continues. So the value of a state equals immediate reward plus discounted value of the next state. This gives rise to the Bellman expectation equation for a given policy P, Vs, famous EP, Rs, A, plus GRI, Vs. In plain terms, the value of state S is the expected reward from taking action, A, as dictated by policy P, plus the discounted value of the resulting state S. Bellman optimality equation. Now comes the twist. What if we want the optimal value, not just one tied to a fixed policy? The Bellman optimality equation removes the policy from the picture. It says V S marsh max over A R S A plus green V S E. Here, we choose the best possible action that gives the highest value, and that's how we find the optimal policy. This recursive structure allows algorithms like value iteration and policy iteration to converge on the best solution. Let's look at how that works. Value iteration. Start with an initial guess for the value of all states. Update each state's value using the Bellman optimality equation. Repeat until the values stabilize. From the final values, extract the optimal policy. It's like tuning a piano. You keep adjusting until every note, state sounds just right. Policy iteration. Start with a random policy. Evaluate how good that policy is using the Bellman expectation equation. Improve the policy by choosing better actions. Repeat until the policy stops changing. This is more like learning by doing, try, evaluate, and improve. Application in artificial intelligence. Now that we know what MDPs and the Bellman equation are, let's see how they are used in real AI systems. Reinforcement learning, RL, is a field of AI where agents learn to make decisions by trial and error, just like a dog learning tricks or a human learning to play chess. MDPs provide the formal structure behind RL. Bellman equations are the backbone of many RL algorithms, including Q-learning deep Q networks, DQN, Sarsa actor-critic models. Example 1, self-driving cars. An autonomous vehicle faces thousands of decisions per minute: when to accelerate, when to brake, how to respond to other cars. Using MDPs, each situation on the road becomes a state. Each driving action is an action. Safety, smoothness, and time saved become the reward. By learning an optimal policy, the car drives safely and efficiently. Example 2, game-playing AI. From AlphaGo to modern chess engines, reinforcement learning based on MDPs has helped machines beat the world's best players. Each move in the game is an action. The board is the state. Winning is the reward. The Bellman equation helps update the value of each possible move. Example 3, robotics. Robots use MDPs to plan their actions in uncertain environments. If the robot slips, that's captured by transition probabilities. Rewards guide it to finish tasks like picking up objects or walking safely. Last but not the least, we began this journey with a simple question: what should I do next? Now we know that answering this question, whether as a robot, a digital assistant, or an AI algorithm, is more than guesswork. It's math, it's strategy, it's intelligence. The Markov decision process gives the world structure. The Bellman equation gives us a way to see the future through recursive logic. Together, they form the brain and spine of many artificial intelligence systems that interact with the world, learn from feedback, and improve over time. But there's something poetic here too. These aren't just dry mathematical ideas, they mimic the way we humans learn and plan. We don't just act randomly, we weigh our options. We consider the consequences, we value the future, even if it's uncertain. In a way, AI, through MDPs and Bellman's legacy, is learning to be a better version of us. So next time you hear about an AI that beats the best gamers, drives a car, or helps a robot deliver groceries, know this: behind it is a decision-making engine built with MDPs and powered by the timeless elegance of the Bellman equation. And now, you know how it works. Until next time, keep learning, stay curious, and remember, intelligence, whether biological or artificial, always begins with one bold step, asking, what should I do next?